Tonight, we're going to explore something that breaks every rule you think you know about how forces work. There's a force inside every atom in your body right now that does something no other force in nature does. When you try to pull two objects apart, this force doesn't weaken, it gets stronger. The harder you pull, the more it fights back. And if you somehow manage to put in enough energy to separate them, something happens that sounds like it belongs in science fiction. The universe itself would rather create entirely new matter out of thin air than let these particles exist alone. This force is not gravity. It's not electromagnetism. It's something far stranger. And understanding it might be the key to understanding why anything in the universe exists at all. Before we dive in, if you find this kind of deep exploration fascinating, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now, let's begin. Let's start with something you already understand. Forces. You deal with forces every single day, even if you don't think about them in scientific terms. When you push a door open, that's a force. When you pick up a coffee mug, that's a force. When you feel the wind against your face on a breezy day, that's a force. When you drop your phone and it falls toward the ground, that's a force pulling it down. Forces are the pushes and pulls that make things move, stop moving, or change direction. They are what make the physical world behave the way it does. Without forces, nothing would happen. Literally nothing. The universe would be a frozen, motionless void, where particles just sat in place forever, never interacting, never combining, never creating anything. Forces are the reason there is action, change, and structure in the cosmos. They are the reason you exist. Now, here's something that might surprise you. Despite the incredible complexity of the universe, despite the staggering variety of phenomena we observe, from lightning bolts to ocean tides to the nuclear reactions inside stars, everything in nature is governed by just 4 fundamental forces. That's it. 4. Every interaction between every particle in the universe, every event that has ever occurred since the beginning of time, can ultimately be traced back to one of these 4 forces. The first 2 are ones you're already familiar with, even if you've never studied physics: gravity and electromagnetism. The other 2 are less well known, but no less important. They're called the weak nuclear force and the strong nuclear force. And tonight, we're going to discover why that last one, the strong nuclear force, is by far the most fascinating, the most counterintuitive, and in certain contexts, the most powerful force in all of nature. But before we can appreciate what makes the strong force so extraordinary, we need to understand how the familiar forces work. Because the strong force breaks almost every pattern the other forces follow, and you can't appreciate how strange something is until you first understand what normal looks like. Let's start with gravity, the force you're most familiar with. Gravity is what keeps your feet on the ground. It's what keeps the moon orbiting the Earth orbiting the sun, and the sun orbiting the center of the Milky Way galaxy. Gravity is the force of attraction between anything that has mass. The more mass something has, the stronger its gravitational pull. The Earth has a lot of mass, about 6 trillion kilograms, so it has a strong gravitational pull. That's why when you jump, you come back down. The Earth is pulling you toward its center. Isaac Newton figured out the mathematics of gravity in the late 1600s. His law of universal gravitation described how every object with mass attracts every other object with mass. The more massive the objects, the stronger the pull. The farther apart they are, the weaker it gets. Albert Einstein later refined this understanding with his general theory of relativity in 1915, revealing that gravity is actually the curvature of space-time caused by mass and energy. But for understanding everyday gravitational behavior, Newton's description works perfectly well. And here's something crucial about gravity. It gets weaker with distance. If you move farther away from a massive object, you feel less of its gravitational pull. This isn't just a gradual decline either. Gravity follows what physicists call the inverse square law. If you double your distance from a massive object, the gravitational force doesn't just drop in half, it drops to 1/4 of what it was. Triple your distance, and it drops to 1/9. This means gravity weakens rapidly with distance. It's why you don't feel the gravitational pull of the sun in your daily life, even though the sun is over 300,000 times more massive than the Earth. The sun is 93 million miles away. And at that distance, its gravity on your body is tiny compared to the Earth's gravity beneath your feet. This inverse square behavior makes intuitive sense. When you hold a magnet close to a metal paperclip, the pull is strong. Move the magnet farther away, and the pull weakens until eventually the paperclip doesn't move at all. Things that are far apart interact weakly. Things that are close together interact strongly. This pattern feels natural. It matches our everyday experience of the world. Gravity also has no limits on its range. It extends outward from every massive object in every direction, reaching across the entire observable universe. It gets weaker and weaker with distance, but it never reaches zero. Technically, the gravitational pull of every star, every galaxy, every particle in the cosmos is reaching you right now. The effect is unimaginably tiny for distant objects, but it's there. Gravity is the sculptor of the cosmos. It's the force that shaped the large-scale structure of the universe, pulling matter together into galaxies, stars, and planets over billions of years. Without gravity, there would be no clumps of matter anywhere. No stars would form. No planets would coalesce. The universe would just be a thin, diffuse cloud of particles spreading out into the darkness forever. But here's the thing about gravity that most people don't realize. In the context of fundamental forces, gravity is extraordinarily weak. Yes, it keeps you pinned to the Earth. Yes, it holds galaxies together. But compared to the other fundamental forces, gravity is almost absurdly feeble. Consider this. Right now, the entire gravitational pull of the Earth, all 6 trillion kilograms of rock and metal and magma beneath your feet, is pulling you downward. And yet, a tiny refrigerator magnet weighing a few grams can hold a paperclip against the Earth's gravity. A few grams of magnet are overpowering the gravitational pull of the entire planet. That's how weak gravity is, compared to electromagnetism, the second fundamental force. Electromagnetism is the force that governs electric charges and magnetic fields. It's responsible for light, for radio waves, for the chemical bonds that hold molecules together, for the electrical signals in your brain that allow you to think, for virtually everything you interact with in daily life that isn't directly related to weight or falling. When you touch a table, the reason your hand doesn't pass through it is electromagnetism. The electrons in the atoms of your hand are repelling the electrons in the atoms of the table. When you see color, that's electromagnetism. Light is an electromagnetic wave. When your heart beats, that's electrical signals propagating through cardiac muscle. When food cooks in a microwave, that's electromagnetic radiation exciting water molecules. When a compass needle points north, that's Earth's magnetic field, which is a consequence of electric currents flowing in Earth's molten iron core. Electromagnetism is everywhere. It is the workhorse of nature at human scales. Like gravity, electromagnetism follows the inverse square law. The electromagnetic force between two charged particles gets weaker as they move apart, dropping with the square of the distance. And like gravity, electromagnetism has infinite range. But unlike gravity, electromagnetism can be both attractive and repulsive. Gravity only pulls. It's always attractive. Every mass attracts every other mass. But electromagnetism has two kinds of charge, positive and negative. Opposite charges attract each other. Like charges repel each other. This gives electromagnetism a flexibility that gravity doesn't have, and it's this flexibility that allows for the incredible complexity of chemistry and biology. In terms of raw strength, electromagnetism is about 10 to the power of 36 times stronger than gravity. That's a 1 followed by 36 zeros. This is an almost inconceivably large number. If you could somehow compare them side by side, the electromagnetic force between two protons would overpower the gravitational force between those same two protons by a factor of about 1 trillion. At the scale of atoms and molecules, gravity is completely irrelevant. It's too weak to matter. Electromagnetism dominates entirely. Now, this brings up an important point. When people ask which is the strongest force, the answer isn't as simple as giving a single name. The forces don't operate on equal footing across all scales. Gravity dominates at cosmic scales because it's always attractive and it accumulates. Planets, stars, and galaxies are made of trillions upon trillions of particles, all pulling each other gravitationally in the same direction. Positive and negative electric charges tend to cancel each other out in large objects, so electromagnetism becomes less dominant at astronomical scales. But at the atomic scale, electromagnetism reigns supreme. Context matters enormously when discussing force strength. So now we have two forces. Gravity, which is weak but universal and shapes the cosmos, and electromagnetism, which is vastly stronger and governs the behavior of atoms, light, and chemistry. Both follow the inverse square law. Both weaken with distance. Both have infinite range. Both behave in ways that feel intuitive to us, even if the mathematics behind them is complex. The third fundamental force is the weak nuclear force. Despite its name, it's actually far stronger than gravity, though weaker than electromagnetism at the subatomic distances where it operates. The weak force is responsible for a specific type of radioactive decay called beta decay, where a neutron inside an atomic nucleus transforms into a proton by emitting an electron and a ghostly particle called a neutrino. This process is essential for the nuclear reactions that power the sun. Without the weak force, hydrogen couldn't fuse into helium in the sun's core, and our star wouldn't shine. Life on Earth wouldn't exist. The weak force has an extremely short range, only about 0.1% of the diameter of a proton. Beyond that tiny distance, the weak force effectively drops to zero. This is because the particles that carry the weak force, called W and Z bosons, are extremely heavy. Their mass limits how far they can travel before they decay, which in turn limits the range of the force. The weak force does its work inside the nucleus and nowhere else. Now, these three forces, gravity, electromagnetism, and the weak nuclear force, all share a common characteristic. They all get weaker with distance in one way or another. Gravity and electromagnetism follow the inverse square law, weakening as you move objects apart. The weak force has such a short range that it barely extends beyond the particles it directly affects. In all three cases, the further apart two objects are, the less they interact. Close together means strong interaction. Far apart means weak interaction or no interaction at all. This pattern feels completely natural. It matches every physical experience you've ever had. Stretch a rubber band and the tension increases, but let it go and move your hands apart and the band goes slack. Hold two magnets close and they snap together. Pull them apart and the pull fades until you can barely feel it. Move away from a campfire and the heat diminishes. Everything in our experience tells us that distance weakens interactions. That's just how the universe works, right? Wrong, because there is a fourth force, and it violates this rule in a way that defies every intuition you have about how forces behave. Let's zoom into the atom, because this is where the story really begins. You probably know the basic structure of an atom from school. At the center is the nucleus, a tiny, dense core. Around the nucleus, electrons orbit in a cloud. The nucleus is incredibly small compared to the atom as a whole. If the atom were the size of a football stadium, the nucleus would be about the size of a marble sitting on the 50-yard line. The rest of the atom is almost entirely empty space. Now, the nucleus itself is made up of two types of particles: protons, which carry a positive electric charge, and neutrons, which carry no electric charge at all. In a simple hydrogen atom, the nucleus is just a single proton. But in heavier elements, the nucleus contains many protons and many neutrons packed together. A carbon nucleus has 6 protons and 6 neutrons. An iron nucleus has 26 protons and 30 neutrons. A uranium nucleus has 92 protons and 146 neutrons. Here's where things get interesting. Remember what electromagnetism tells us? Like charges repel each other. Protons are all positively charged. Every single proton in a nucleus carries the same positive charge, and they're packed together in an incredibly tiny space, separated by distances of roughly 1 femtometer, which is 1 quadrillionth of a meter. That's a decimal point followed by 14 zeros, and then a 1. To give you a sense of how small that is, a femtometer is to a meter what a meter is to roughly the distance from Earth to a point beyond the nearest star. At these distances, the electromagnetic repulsion between protons is enormous. Absolutely enormous. They should be violently pushing each other apart. An iron nucleus with its 26 protons crammed together should explode instantly. The electromagnetic repulsion at these distances is tremendous. Every proton is screaming to get away from every other proton. The force trying to blow the nucleus apart is staggering, and yet the nucleus holds together. Not just barely holds together, it holds together with extraordinary stability. Iron nuclei have existed since they were forged inside massive stars billions of years ago. They don't fly apart. They don't slowly disintegrate. They sit there, stable, as if the ferocious electromagnetic repulsion between their protons simply doesn't matter. Something is overpowering electromagnetism. Something is holding those protons and neutrons together despite the enormous electromagnetic force trying to tear them apart. And whatever that something is, it must be extraordinarily powerful, because electromagnetism is no weakling. We already established that electromagnetism is 10 to the 36 times stronger than gravity. Whatever force is holding the nucleus together must be even stronger than electromagnetism at these scales. at least strong enough to overwhelm it completely. This is the strong nuclear force, the fourth and final fundamental force of nature. And in the context of holding atomic nuclei together, it's the most powerful force we know of. But here's the first strange thing about the strong force. You've never felt it. Not once in your entire life. Despite it being so incredibly powerful, despite it operating inside every single atom in your body right now, you have absolutely no direct experience of it. You feel gravity every time you take a step. You experience electromagnetism every time you see light or touch an object or feel the warmth of the sun. But the strong force is completely invisible to your daily experience. Why? Because the strong force has an incredibly short range. Unlike gravity and electromagnetism, which reach across the entire universe, the strong force operates only at distances of about 1 femtometer, roughly the diameter of a proton. Beyond that distance, it drops off so sharply that it effectively ceases to exist. This is why you don't feel it. It never reaches beyond the atomic nucleus. It's like a guard that operates only inside a locked room. It's incredibly strong within that room, strong enough to overpower anything else that tries to operate there. But it never steps outside. It never affects the larger world. This short range is what makes the strong force so different from gravity and electromagnetism. Those forces extend outward forever, getting weaker but never truly disappearing. The strong force is confined to the tiniest scales in the universe. It does its work inside a space so small that you could line up 1 trillion protons side by side, and they'd only stretch about 1 millimeter. At the scale of the nucleus, the strong force doesn't just compete with electromagnetism, it dominates. The strong force between 2 protons at nuclear distances is roughly 100 times stronger than the electromagnetic repulsion between them. This is why nuclei hold together. The strong force simply overpowers the electromagnetic repulsion, binding protons and neutrons into a dense, stable cluster. But this picture of the strong force, the version you might have learned in school, is actually only part of the story. It's what physicists call the residual strong force, or the nuclear force. It's the force as it appears at the scale of protons and neutrons. It's real and it's important, but it's not the fundamental version of the strong force. It's more like an echo, a shadow, a side effect of something much deeper and much stranger happening inside the protons and neutrons themselves. Because protons and neutrons are not fundamental particles. They're not the smallest things that exist. They're made of even smaller particles. And the true strong force, the fundamental strong force, operates between those smaller particles in ways that are utterly unlike anything else in physics. To understand the strong force in its true form, we need to go deeper. We need to go inside the proton itself. We need to enter a world where the rules of everyday physics break down completely. A world where the force between 2 particles doesn't weaken when you pull them apart, it gets stronger. A world where particles are imprisoned by the very fabric of reality, confined to a space so small that they can never be observed in isolation, no matter how much energy you throw at the problem. A world where the universe would rather spontaneously create new matter than allow certain particles to exist on their own. This is the world of quarks and gluons, and the theory that describes their interactions is called quantum chromodynamics, one of the most successful and most bizarre theories in all of physics. When physicists first started probing the internal structure of protons and neutrons in the 1950s and 60s, they discovered something unexpected. The proton wasn't a simple, solid ball of matter. It had structure inside it. There were smaller things moving around in there. This was shocking. For decades, protons and neutrons had been considered fundamental, indivisible particles. The very word atom comes from the Greek word atomos, meaning uncuttable. But atoms turned out to be made of smaller parts. And now even those smaller parts, the protons and neutrons, turned out to have parts of their own. It was like opening a Russian nesting doll and finding yet another doll inside. These experiments, conducted at places like the Stanford Linear Accelerator Center in California, involve firing extremely high-energy electrons at protons and watching how they scattered. If a proton were a solid, uniform sphere, the electrons would scatter in a smooth, predictable pattern. But that's not what happened. Instead, the electrons scattered as if they were bouncing off small, hard, point-like objects inside the proton. Something was in there. The theoretical framework to explain what was inside the proton came from a physicist named Murray Gell-Mann. In 1964, Gell-Mann proposed that protons, neutrons, and all similar particles were made of smaller constituents, which he called quarks. The name came from a line in James Joyce's novel Finnegan's Wake, 3 quarks for muster mark. It was a whimsical name for a revolutionary idea. Gell-Mann proposed that there were 3 types or flavors of quarks. He called them up, down, and strange. A proton, he said, was made of 2 up quarks and 1 down quark. A neutron was made of 2 down quarks and 1 up quark. Other, more exotic particles observed in cosmic rays and particle accelerators were made of different combinations of these 3 quark flavors. The theory was elegant and it explained the patterns physicists had been seeing in particle experiments. But many physicists were skeptical. Were quarks real particles, or were they just mathematical bookkeeping devices? Convenient fictions that helped organize the data without actually existing as physical objects? The answer came from experiments. In 1968 and 1969, a series of groundbreaking experiments at the Stanford Linear Accelerator Center provided the first direct evidence that quarks were real. These experiments, called deep inelastic scattering experiments, fired extremely high-energy electrons at protons. The word deep refers to the fact that the electrons were penetrating deep inside the proton, not just bouncing off its surface. And inelastic means the collisions were violent enough to disrupt the proton's internal structure. The electrons penetrated deep inside the protons and scattered off something small and hard inside. The scattering patterns were exactly what you'd expect if the protons contained 3 point-like objects, each carrying a fraction of the proton's total momentum. It was as if the physicists had been throwing tennis balls at what they thought was a smooth balloon, only to discover the balls were bouncing off tiny marbles hidden inside. The physicists conducting these experiments, Jerome Friedman, Henry Kendall, and Richard Taylor, later shared the 1990 Nobel Prize in Physics for this discovery. Quarks were real. They weren't just mathematical conveniences. They were actual physical objects inside the proton. Since then, physicists have discovered 6 flavors of quarks in total: up and down, which make up ordinary matter, strange and charm, which are heavier, and bottom and top, which are heavier still. The top quark is the heaviest fundamental particle ever discovered, with a mass roughly 185 times that of a proton. Despite this variety, the matter you interact with every day, the atoms in your body, the air you breathe, the ground beneath your feet, is made entirely of up quarks and down quarks. the heavier quarks are unstable and decay almost instantly into up and down quarks. They only exist for fleeting moments in high-energy particle collisions, either in particle accelerators or in cosmic ray showers. Now, if quarks are real and they exist inside protons and neutrons, there must be a force that holds them together inside the proton. This force is the true strong force, not the residual nuclear force that holds the nucleus together, but the fundamental interaction between quarks. And this force is carried by particles called gluons, named for the obvious reason that they glue quarks together. But the strong force between quarks, described by the theory of quantum chromodynamics, is nothing like any force you've ever encountered. It doesn't behave like gravity. It doesn't behave like electromagnetism. It doesn't even behave like the residual nuclear force that holds protons and neutrons in the nucleus. The strong force between quarks is something entirely new, something that challenges our most basic assumptions about how forces should work. And to understand why, we need to talk about a property that quarks possess, a property that has no analogy in everyday life. It's called color charge, not color as in red, blue, or green light. Color charge has nothing to do with actual visible color. It's just a label physicists gave to a property of quarks that comes in 3 varieties. And since 3 primary colors seemed like a convenient naming convention, the name stuck. Each quark carries one of 3 color charges, which physicists label red, green, or blue. Antiquarks carry the corresponding anticolors: anti-red, anti-green, and anti-blue. And the rule of the strong force, the fundamental rule that governs how quarks combine, is this: only colorless combinations of quarks can exist as free particles. A proton is colorless because it contains 1 red quark, 1 green quark, and 1 blue quark. Red plus green plus blue equals white, which is colorless. A meson, another type of particle, is colorless because it contains a quark and an antiquark, whose colors cancel out. Red plus anti-red equals colorless. This color neutrality rule is absolute. Nature enforces it with total, uncompromising rigidity. You cannot have a free particle that carries a net color charge, ever. And the mechanism by which nature enforces this rule is the most extraordinary thing about the strong force. It's something we're going to explore in depth. Because the way the strong force ensures that quarks never appear alone, the way it confines them, the way it behaves when quarks try to separate, is unlike anything else in all of physics. And it starts with a single remarkable fact. Gluons, the particles that carry the strong force, are themselves affected by the strong force. This is the key. This is what makes the strong force unique among all the fundamental forces. Photons carry electromagnetism, but photons don't have electric charge. They don't interact with each other electromagnetically. They just pass through each other. Gravitons, if they exist, would carry gravity, but they wouldn't interact gravitationally with each other in any significant way. But gluons carry color charge. Gluons themselves are colored, and because they carry color charge, gluons interact with other gluons. They attract each other. They pull on each other. The force carriers are affected by their own force. This seemingly small detail, this self-interaction of gluons, changes everything. It's responsible for every strange property of the strong force. It's why the strong force gets stronger with distance instead of weaker. It's why quarks can never be free. It's why the universe creates new matter rather than allowing isolated quarks to exist. All of it traces back to this one fact. Gluons interact with each other, and we are just getting started. To understand just how radical that gluon-self interaction is, and why it makes the strong force behave like nothing else in nature, we need to take a step back and look at how forces work at the quantum level. Because at the subatomic scale, forces don't operate the way you might imagine. There are no invisible ropes pulling particles together. There are no mysterious fields just pushing things around in some abstract way. Instead, forces are carried by particles. Actual physical particles that travel between the objects being affected by the force. This idea is one of the central pillars of modern physics, and understanding it is the key to understanding why the strong force is so profoundly different from everything else. In quantum field theory, which is the mathematical framework that describes all fundamental forces except gravity, every force is mediated by what physicists call gauge bosons. These are particles that carry the force between other particles. The concept might sound abstract, but there's a simple way to picture it. Think of it like two ice skaters standing on a frictionless surface, tossing a basketball back and forth. Every time one skater throws the ball, they recoil backward from the throw. Every time the other skater catches the ball, they get pushed backward by the impact. The two skaters end up moving apart, pushed by the exchange of the basketball. This is a rough analogy for how repulsive forces work at the quantum level. Attractive forces are harder to visualize with this analogy, but the core idea remains the same. Forces arise from the exchange of particles between the objects experiencing the force. The particles doing the traveling are the gauge bosons, the force carriers. For electromagnetism, the force carrier is the photon. When two electrons repel each other, what's actually happening at the quantum level is that they're exchanging virtual photons. These virtual photons aren't the same as the real photons that make up visible light. You can't see them or detect them directly. They exist for an incredibly brief time, popping into existence, traveling between the two electrons, and transferring a momentum before vanishing. But their effect is real and measurable. The electromagnetic force is a result of this constant exchange of virtual photons between charged particles. The more photons exchanged, the stronger the force. For the weak nuclear force, the force carriers are the W and Z bosons. These are extremely heavy particles, about 86 to 97 times the mass of a proton. Their heaviness is the reason the weak force has such a short range. Heavy particles can only travel a very short distance before they decay, which limits how far the force can reach. The W and Z bosons were predicted theoretically in the 1960s and discovered experimentally at CERN in 1983, earning Carlo Rubbia and Simon van der Meer the 1984 Nobel Prize in Physics. For gravity, the hypothetical force carrier is called the graviton. Gravitons have never been detected, and many physicists aren't sure they ever will be. Gravity is so weak compared to the other forces that detecting individual gravitons would require technology far beyond anything we currently have or can even conceive of building. But in theoretical frameworks that attempt to reconcile gravity with quantum mechanics, the graviton is the particle that would mediate gravitational interactions. And for the strong force, the force carriers are gluons, 8 different types of gluons to be precise. This number isn't arbitrary. It comes from the mathematics of the symmetry group that describes the strong force, called SU3. This is a mathematical structure that governs how 3 color charges interact. The mathematics dictates that there must be exactly 8 independent gluon states, each carrying a different combination of color and anti-color charge. For example, One gluon might carry a combination of red and anti-blue. Another might carry green and anti-red. The combinations are specific and mathematically determined. The 8 gluon types work together to mediate the strong force between quarks, constantly being exchanged inside every proton and neutron in the universe. Now, here's where we arrive at the crucial difference, the difference that makes the strong force unlike anything else. And I need you to really focus on this, because everything that follows depends on understanding this one point. Remember, photons carry electromagnetism, but they don't carry electric charge. They're neutral messengers. This is why 2 beams of light can pass right through each other without any interaction. You can shine 2 flashlights so their beams cross, and neither beam affects the other. Photons deliver the force, but they're not affected by it themselves. Gluons are fundamentally different. Gluons carry color charge. They are not neutral messengers, they are charged participants. Every single gluon carries a color and an anticolor. This means gluons are affected by the very force they carry. A gluon can interact with another gluon. A gluon can emit another gluon. A gluon can absorb another gluon. Gluons can even interact with themselves in complex loops and chains. The force carriers are tangled up in their own force. Let me try to make this concrete with an analogy, even though no analogy is perfect for something this strange. Imagine you're trying to send a message to someone across a room by throwing tennis balls to a messenger who carries them over. In electromagnetism, the messenger is invisible and unaffected by the tennis balls. They just carry the balls back and forth without interacting with them in any way. The exchange is clean and straightforward. Now, imagine the same scenario, but this time, the messenger is also made of tennis balls. And as the messenger walks across the room, they keep getting hit by other tennis balls, and they keep throwing new tennis balls in random directions, which then create more messengers, who create more tennis balls. The simple exchange has become a chaotic, self-reinforcing mess. That's closer to what happens with a strong force. The gluons that carry the force are themselves sources of the force, creating new gluons, which create more gluons, which interact with each other in an ever-growing web of interactions. This self-interaction has consequences that are absolutely staggering. It fundamentally changes how the force behaves with distance. And to understand why, we need to dive into one of the most beautiful and strange ideas in all of quantum physics. The idea that empty space isn't really empty. When you think of a vacuum, you probably think of nothing. Empty space. A void with absolutely nothing in it. But quantum mechanics tells us this picture is completely wrong. The vacuum, what we call empty space, is actually a seething, roiling ocean of activity. Particles and antiparticles are constantly popping into existence in pairs, existing for the tiniest fraction of a second, and then annihilating each other and disappearing again. These are called virtual particles, and they exist because of the Heisenberg uncertainty principle. The uncertainty principle says that you can't simultaneously know certain pairs of properties with perfect precision. One version of this principle relates energy and time. It says that over very short time intervals, the energy of a system can fluctuate by a large amount. This means that for very brief moments, enough energy can appear out of nowhere to create a particle-antiparticle pair. These particles don't violate conservation of energy because they exist for such a short time that the universe essentially doesn't notice the temporary energy loan. They borrow the energy, exist for an instant, and then pay it back by annihilating each other. This sounds bizarre, but It's not speculation. Virtual particles have measurable effects. One of the most famous is the Casimir effect, predicted by Dutch physicist Hendrik Casimir in 1948. If you place two uncharged metal plates very close together in a vacuum, there's a measurable attractive force between them. This force exists because the virtual particles between the plates are slightly more constrained than the virtual particles outside the plates, creating a pressure difference that pushes the plates together. The Casimir effect has been measured in laboratories with extraordinary precision, and it matches the theoretical predictions perfectly. Another measurable effect of virtual particles is the Lamb shift, a tiny difference in the energy levels of hydrogen atoms that was first detected by Willis Lamb and Robert Rutherford in 1947. The Lamb shift exists because virtual particles briefly alter the electromagnetic field around the electron in a hydrogen atom, shifting its energy levels by a tiny but measurable amount. These are not abstract theoretical curiosities. They are real physical effects that have been confirmed in laboratories around the world. Empty space is not empty. It's alive with quantum fluctuations. Now, here's why this matters for understanding force strength. These virtual particles that constantly pop in and out of existence in the vacuum can affect how forces behave. When you have a charged particle like an electron sitting in space, the virtual particle-antiparticle pairs that constantly appear around it respond to its charge. Virtual positrons, which are positively charged, are attracted toward the electron. Virtual electrons are repelled away from it. This creates a cloud of virtual particles around the real electron, with the positive virtual particles slightly closer and the negative ones slightly farther away. This cloud of virtual particles partially shields the electron's charge. From a distance, the electron's charge appears weaker than it actually is because the virtual particle cloud is screening it. The positive virtual particles cluster close to the electron, partially cancelling its negative charge from the perspective of anything far away. But if you get very close to the electron, if you penetrate inside the cloud of virtual particles, you see the full, unshielded charge. The electron's charge appears stronger at close range and weaker at long range because of this screening effect. This phenomenon is called vacuum polarization, and it's been measured with incredible precision. It's one of the great triumphs of quantum electrodynamics, or QED, the quantum theory of electromagnetism, developed primarily by Richard Feynman, Julian Schwinger, and Shinichiro Tomonaga in the late 1940s. All three shared the 1965 Nobel Prize for this work. QED predicts that the effective electric charge of an electron should change slightly depending on how closely you probe it. At very short distances, probed with very high energy experiments, the electron's charge appears slightly stronger than it does at longer distances. This has been confirmed experimentally to an accuracy of about 1 part in a trillion. QED is sometimes called the most precise theory in all of science because of how accurately its predictions match experimental measurements. It is the gold standard for quantum field theories, and when physicists set out to build a quantum theory of the strong force, QED was the template they tried to follow. The theory they built, quantum chromodynamics, follows the same general mathematical structure as QED. But because gluons carry charge and photons don't, the predictions of QCD turn out to be radically, almost shockingly different. So in electromagnetism, vacuum polarization screens the charge. Virtual particles make the charge appear weaker at long range. The closer you get to a charged particle, the stronger the charge appears. The farther away you are, the weaker it appears. This makes intuitive sense. It's consistent with our everyday experience. Forces are weaker at distance and stronger up close. Now let's turn to the strong force and quantum chromodynamics, or QCD. The same thing happens in QCD. Virtual quark-antiquark pairs pop in and out of the vacuum around a color-charged quark. These virtual quarks respond to the color charge of the real quark, creating a screening effect similar to what happens in QED. If this were the only effect, the strong force would behave just like electromagnetism. The color charge would be screened at long distances and appear stronger at short distances. It would weaken with distance, just like every other force, but it's not the only effect, because gluons carry color charge. In QED, photons don't carry electric charge, so they don't contribute to the screening cloud around an electron. Photons are neutral. They deliver the force, but don't add to the charge distribution. The only things screening the electron's charge are the virtual electron-positron pairs. In QCD, gluons carry color charge. So in addition to virtual quark-antiquark pairs popping in and out of the vacuum, virtual gluons are also appearing and disappearing. And these virtual gluons don't screen the color charge. They do the opposite, they anti-screen it. The virtual gluons around a color-charged quark actually spread the color charge out, smearing it over a larger region of space. Instead of concentrating the charge and making it appear weaker from far away, the gluons disperse it and make it appear stronger from far away. This anti-screening effect from gluons competes with the screening effect from virtual quarks. And here's the critical point. The gluon anti-screening effect wins. It doesn't just slightly win. It overwhelmingly dominates. The anti-screening from gluons is so much stronger than the screening from quarks that the net effect is the exact opposite of what happens in electromagnetism. In QCD, the effective color charge gets weaker at short distances and stronger at long distances. The closer two quarks are to each other, the weaker the force between them. The farther apart they are, the stronger the force becomes. This is the exact opposite of every other force in nature. Every other force gets weaker with distance, the strong force gets stronger. And this reversal, this inversion of the normal pattern, is entirely due to the fact that gluons carry color charge and interact with each other and with the vacuum in ways that photons simply don't. Let me pause here and make sure you understand just how revolutionary this is. We've already seen that every other force in nature weakens with distance. That pattern is so deeply embedded in our experience of the world that we take it for granted. We assume it's just how forces work. It seems like a law of nature, something fundamental and universal. But the strong force tells us that this pattern is not universal. It's not a law of nature. It's just how some forces happen to work. The strong force obeys a completely different pattern, one where distance strengthens the interaction instead of weakening it. And this different pattern exists because of a single property that gluons have and photons don't: color charge. The ability of force carriers to interact with each other. That one difference changes everything. Now, the theory of quantum chromodynamics wasn't developed overnight. It was the product of decades of work by some of the most brilliant physicists of the 20th century. The story of QCD is a story of puzzle pieces gradually coming together, of experimental clues accumulating over years, and of theoretical breakthroughs that transformed our understanding of the subatomic world. After Murray-Gell-Mann proposed the quark model in 1964, and after the deep inelastic scattering experiments at Stanford confirmed that quarks were real, physicists faced a serious problem. The quark model worked beautifully in many respects. It explained the patterns of particles that had been discovered in cosmic ray experiments and particle accelerators. It predicted new particles that were later found. But there was a glaring inconsistency that threatened to undermine the entire theory. The problem involved a particle called the delta++ baryon. This particle was known to contain 3 up-quarks, and according to quantum mechanics, each of these quarks should have the same spin orientation. But the Pauli exclusion principle, one of the bedrock laws of quantum mechanics, says that no 2 identical fermions can occupy the same quantum state. This principle isn't just a theoretical abstraction. It's the reason the periodic table works. It's the reason atoms have different sizes and chemical properties. It's the reason solid matter doesn't collapse into a single point. The Pauli exclusion principle is fundamental to the structure of everything around you. Fermions are particles with half-integer spin, and quarks are fermions. 3 up quarks with the same spin in the same location would be 3 identical fermions in the same quantum state. This is forbidden by the Pauli exclusion principle. Absolutely, unambiguously forbidden. It should be impossible. The delta++ baryon shouldn't exist. But it did exist. It had been detected in experiments multiple times. It was real and reproducible. So either the Pauli exclusion principle was wrong, which would upend virtually all of quantum mechanics and invalidate countless successful predictions, or the quarks were not actually identical. There had to be some additional property, some hidden quantum number, some invisible label that distinguished the 3 up quarks from each other, making them different despite having the same flavor and spin. This is where color charge entered the picture. In 1964, physicist Oscar Greenberg proposed that quarks carry an additional quantum number that comes in 3 varieties. The following year, Mu-Young Han and Yoichiro Nambu developed a related model with a similar 3-valued charge. Greenberg initially called this property parastatistics, but it was eventually given the more evocative name of color charge by Gell-Mann. The name was inspired by the analogy with color mixing. Just as the 3 primary colors of light, red, green, and blue, combine to make white light, the 3 color charges combine to make a colorless particle. If each of the 3 up quarks in the delta++ baryon carries a different color charge, 1 red, 1 green, and 1 blue, then they are no longer identical. They differ in this newly discovered property. The Pauli exclusion principle is satisfied. The puzzle is solved. But color charge wasn't just a clever bookkeeping trick invented solely to save the Pauli exclusion principle. It turned out to be something far more significant and fundamental. It turned out to be the actual physical charge of the strong force, just as electric charge is the physical charge of electromagnetism. The strong force acts on particles that carry color charge, just as electromagnetism acts on particles that carry electric charge. And the mathematics of how 3 color charges interact is described by a branch of mathematics called group theory, specifically by the symmetry group S mu3. The full theory of quantum chromodynamics was developed primarily in the early 1970s. Several physicists contributed to its development, including Murray-Gell-Mann himself, Harold Fritsch, and Heinrich Leutwiler, who helped formulate the SU3 gauge theory structure. But the key breakthrough, the one that made QCD a viable and testable theory, came in 1973, when three physicists working independently made a discovery that would earn them the Nobel Prize in Physics 3 decades later. David Gross and his graduate student Frank Wilczek at Princeton University and David Politzer at Harvard University independently calculated how the strong force's coupling constant, essentially a number that measures its strength, changes with energy scale. A coupling constant isn't really a constant at all in quantum field theory. It runs, meaning it changes depending on the energy at which you measure it. In QED, the electromagnetic coupling constant increases very slowly with energy. But when Gross, Wilczek, and Politzer performed the equivalent calculation for QCD, their results showed something that stunned the physics community. The strong force's effective strength decreases at higher energies, which correspond to shorter distances. At very short distances, deep inside the proton, the strong force becomes weak. Quarks at very close range barely interact with each other. They behave almost as if they're free particles, unbound and independent. This was completely unprecedented. No other quantum field theory had ever shown this behavior. This property was given the name asymptotic freedom. Asymptotic meaning approaching a limit, and freedom meaning the quarks become effectively free. At infinitely short distances, in the limit where quarks are right on top of each other, the strong force approaches zero. The quarks become asymptotically free. This was the explanation for something that had been puzzling physicists for years. The deep inelastic scattering experiments at Stanford had shown that quarks inside the proton behaved as if they were free particles, barely interacting with each other. This was paradoxical because if the strong force was supposed to be holding quarks together inside the proton, how could the quarks appear to be free? The answer was asymptotic freedom. When the high-energy electrons probed the proton at very short distances, they were seeing the quarks in a regime where the strong force was weak. At those tiny distances, the quarks were nearly free. The strong force was still there, but it was so weak at those scales that the quarks moved almost independently. But here's the flip side of asymptotic freedom, and this is the part that makes the strong force truly terrifying in its implications. If the force gets weaker at short distances, it must get stronger at longer distances. And it does. As you try to pull two quarks apart, as the distance between them increases, the strong force grows. It doesn't just increase a little, it increases dramatically. The farther apart the quarks get, the stronger the force pulling them back together becomes. This is the opposite of stretching a spring or a rubber band. When you stretch a spring, the restoring force increases, but there's a limit. Eventually the spring breaks, the material gives way, the force reaches a maximum and then drops to zero when the spring snaps. The strong force doesn't do this. It just keeps getting stronger. There is no maximum. There is no point where the gluon field snaps and lets the quarks go free. As you put more and more energy into separating two quarks, the force between them grows and grows without limit. Think about what this means practically. Imagine you could somehow grab hold of two quarks inside a proton and try to pull them apart. At first, when they're close together, the force between them is relatively mild. The quarks are nearly free, moving around inside the proton with considerable independence. But as you start to separate them, the force increases. You pull harder, and the force resists more strongly. You put in more energy and the resistance grows even more. The more energy you invest in trying to separate these quarks, the stronger the force pulling them back together becomes. It's like being trapped in quicksand that gets denser the harder you struggle. Every attempt to escape just makes the trap stronger. This leads to what might be the most extraordinary phenomenon in all of physics. Something happens when you put enough energy into trying to separate quarks, but that revelation deserves to be explored fully. So let's build up to it carefully. What happens when you push this process to its extreme? When you pump enormous amounts of energy into trying to pull quarks apart? Is something so counterintuitive, so wildly strange, that it fundamentally challenges our understanding of what it means to take something apart. And it's been confirmed in some of the most powerful experiments ever conducted by human beings. In particle colliders that recreate conditions not seen since the first microseconds after the Big Bang itself. Before we get there, let me summarize where we stand. We've discovered that the strong force, mediated by gluons, is fundamentally different from every other force in nature. The key difference is that gluons carry color charge and interact with each other. This self-interaction causes the vacuum around color-charged quarks to behave in the opposite way from the vacuum around electrically charged particles. Instead of screening the charge and making it weaker at long range, the gluon-filled vacuum anti-screens the color charge, making it stronger at long range. This produces asymptotic freedom, where quarks are nearly free at short distances, and an ever-increasing force at longer distances. We've also seen how this theory, quantum chromodynamics, came together over decades. From Gell-Mann's quark model to the resolution of the Pauli exclusion problem through color charge, to the development of the full SU3 gauge theory, to the discovery of asymptotic freedom by Gross, Wilczek, and Politzer. Each step built on the last, each puzzle piece clicking into place to reveal a picture of the strong force that is both mathematically elegant and physically bizarre. The strong force doesn't play by the rules that the other forces follow. It has written its own rules, and those rules have consequences that are so strange, so far outside our everyday experience, that even physicists who have studied them for decades still find them remarkable. So now let's confront those consequences directly. What happens when the strong force refuses to let go? What happens when quarks try to escape the grip of the gluon field? And what happens when the universe itself intervenes to ensure that certain particles can never, under any circumstances, exist alone? Because that's the real mystery of the strong force. Not just that it's powerful, not just that it gets stronger with distance, but that it creates a prison from which there is no escape. A prison that no amount of energy can break open. A prison where the walls grow thicker the harder you push against them. And a prison where, if you somehow manage to force a crack in the wall, the universe instantly builds a new wall to replace it, creating new matter in the process. This phenomenon is called confinement, and it is one of the strangest, most profound and least understood aspects of the physical world we live in. It is also, incredibly, the reason you exist. The reason atoms exist. The reason matter has the mass it does. The reason stars can burn and planets can form, and life can emerge from the chaos of the early universe. Everything traces back to this one extraordinary force and its refusal to let go. So here we are at the heart of the mystery. We know that the strong force gets stronger as quarks are pulled apart. We know that gluon self-interaction causes the vacuum to anti-screen color charge, making the force grow with distance instead of shrink. We know that quarks are nearly free when they're close together, but increasingly trapped as they try to separate. But what actually happens when you try to pull two quarks apart? What does the strong force do when it's pushed to its limits? The answer is one of the most extraordinary phenomena in all of physics. And to understand it, we need to look at what happens to the gluon field between two separating quarks. In electromagnetism, when you place two opposite electric charges near each other, the electric field lines spread outward in all directions between them. The field fills the space between the charges and extends into the surrounding space as well. The field lines fan out, spreading over a wider and wider area as they extend between the two charges. This spreading is part of the reason the electromagnetic force weakens with distance. The field energy is distributed over a larger and larger volume, so the force per unit area decreases. It's like the light from a flashlight. Close to the flashlight, the beam is concentrated and bright. Farther away, the beam is spread out and the light is dimmer. The same total energy is there, but it's spread over a much larger area. The gluon field between two quarks behaves in a completely different way. Strikingly, radically different. Instead of spreading out in all directions, the gluon field lines between two separating quarks squeeze together. They compress into a narrow, concentrated tube connecting the two quarks. Physicists call this a flux tube, or sometimes a color string. As you pull the quarks farther apart, this tube doesn't spread out or dissipate. It stays narrow. It stays concentrated. It stretches between the two quarks like an elastic band, maintaining roughly the same diameter no matter how long it gets. The energy stored in this flux tube is approximately proportional to its length. This is a key point, so let me emphasize it. Double the distance between the quarks, and you roughly double the energy stored in the tube. Triple the distance, triple the energy. The energy grows linearly with distance, which means the force between the quarks remains roughly constant regardless of how far apart they are. This is radically different from the inverse square law that governs gravity and electromagnetism. Why does the gluon field do this? Why does it squeeze into a tube instead of spreading out like the electromagnetic field? The answer goes back to gluon self-interaction. Because gluons carry color charge and interact with each other, the gluon field lines attract one another. In electromagnetism, field lines repel each other, which is why they spread out. But in the strong force, the field lines pull toward each other, squeezing into a tight bundle. The self-interaction of gluons creates a kind of pressure that keeps the field lines confined to a narrow region. The gluons are literally holding each other together, forming a coherent structure, a string of gluonic energy connecting the two quarks. This flux tube has remarkable properties. It's incredibly thin, only about 1 femtometer in diameter, roughly the size of a proton, but it can stretch to much longer lengths as the quarks separate. And the energy density inside the tube is enormous. The tension in this color string is about 14 tons. Let me say that again because it sounds so improbable. The tension in the gluon flux tube connecting two quarks is approximately 14 metric tons of force. That's roughly the weight of 2 full-grown African elephants, concentrated in a tube thinner than an atomic nucleus. The amount of force packed into this microscopic structure is staggering. It's the strongest tension of any known physical object in the universe. Now, imagine you keep pulling the quarks apart. The flux tube stretches, energy accumulates in the tube. You're pumping more and more energy into the system, and that energy is being stored in the gluon field between the quarks. The tube gets longer and longer, and the total energy stored in it increases and increases. At some point, the energy stored in the flux tube becomes enormous. And here is where something truly astonishing happens. Something that sounds like it shouldn't be possible. Something that violates every intuition you might have about what it means to pull two things apart. The energy in the flux tube becomes so large that it exceeds the threshold needed to create new particles. Remember Einstein's famous equation, E equals mc squared. Energy and mass are interchangeable. If you concentrate enough energy in one place, that energy can spontaneously convert into matter, specifically into a quark-antiquark pair. So as you stretch the flux tube between two quarks, at some point the tube snaps, but it doesn't snap the way a rubber band snaps, leaving you with two separate ends and nothing in between. When the flux tube snaps, a new quark and a new antiquark are created at the breaking point. The energy stored in the tube is converted directly into the mass and kinetic energy of these new particles. And here's the crucial part. The new quark pairs up with one of the original quarks, and the new antiquark pairs up with the other original quark. You start with two quarks connected by a flux tube. You tried to separate them. And instead of getting two free quarks, you got two new quark-antiquark pairs. Two new composite particles. You haven't freed the quarks, you've just created more quarks. This is like trying to separate the north and south poles of a magnet by breaking it in half. When you snap a bar magnet, you don't get an isolated north pole and an isolated south pole. You get two smaller magnets, each with its own north and south pole. No matter how many times you break the magnet, you always end up with complete magnets, never an isolated pole. The strong force does the same thing with quarks, but the mechanism is far more dramatic. Instead of just rearranging existing material, the strong force creates entirely new matter from pure energy. No matter how hard you try to separate quarks, no matter how much energy you put in, you always end up with complete, colorless composite particles, never a free quark. The energy you invested didn't help you isolate the quarks. It just made more quarks. You've been defeated by the very energy you brought to the fight. This phenomenon is called color confinement, and it is one of the deepest and most absolute properties of the strong force. Color confinement means that particles carrying a net color charge can never exist as free isolated objects under any circumstances. Quarks always come in colorless combinations. Either three quarks combining red, green, and blue to make a baryon like a proton or neutron, or a quark and an antiquark combining a color with its anticolor to make a meson. You cannot have a free quark. The universe forbids it. Not as a practical matter, not because we lack the technology. The universe forbids it as a matter of fundamental physics. The very structure of the strong force makes it impossible. No free quark has ever been observed. Not in any particle accelerator on Earth. Not in any cosmic ray observation. Not in any laboratory experiment anywhere in the world. Not anywhere in the universe as far as we can tell. Physicists have searched extensively and creatively for decades. In the 1960s and 70s, multiple experiments searched for free quarks by looking for particles with fractional electric charge. Quarks carry charges of either positive 2/3 or negative 1/3 of the electron's charge. Any free quark would have a distinctive fractional charge that's easy to distinguish from the integer charges carried by all known free particles. If a free quark existed anywhere in ordinary matter, its fractional charge would stick out like a sore thumb in any sensitive electrical measurement. Experimenters looked in cosmic rays bombarding Earth from space. They looked in pond water and ocean water. They looked in lunar soil samples brought back by the Apollo missions, reasoning that the moon's surface, bombarded by cosmic rays for billions of years, might have accumulated free quarks if they existed. They searched in ancient meteorites that had traveled through interstellar space. They looked in deep ocean sediments deposited over millions of years. They searched in particle accelerator debris from the highest energy collisions available. Some experimenters even searched in the fallout from nuclear weapons tests, thinking that the extreme conditions of a nuclear explosion might have liberated quarks. Nowhere did they find any evidence of fractional charges. Every single search came up empty. This decades-long absence of free quarks is not a failure of experimental physics. It's a resounding confirmation of color confinement. Free quarks don't exist because they can't exist. The strong force won't allow it. Now, this leads to a remarkable process that physicists observe every day in particle accelerators around the world. When high-energy particles collide, when protons smash into each other at nearly the speed of light, quarks inside the colliding protons are knocked loose. They fly off in different directions, carrying enormous kinetic energy, but they can't travel alone. Color confinement is absolute. As a quark flies away from the collision point, it trails a flux tube behind it, connected to the other quarks from the smashed proton. Energy builds up in the tube. The tube snaps, creating new quark-antiquark pairs. Those new quarks form their own flux tubes, which also snap, creating even more quarks. This cascading process happens incredibly quickly, in roughly a trillionth of a second. The result is a spray of composite particles, protons, neutrons, pions, kaons, and other hadrons, all flying in roughly the same direction as the original quark. Physicists call this spray a jet, and these jets are one of the most striking and beautiful phenomena observed in particle physics experiments. When you look at the data from a particle collider like the Large Hadron Collider at CERN, you don't see quarks, you see jets. Tightly focused sprays of particles all traveling in the same direction, betraying the path of the original quark that created them. The quark itself is long gone, absorbed back into the web of confinement, but its ghost remains in the form of the jet, a signature of the quark's brief moment of freedom before the strong force pulled it back into captivity. By studying these jets, physicists can infer the properties of the quarks that created them. The energy of the jet tells you the energy of the quark. The direction tells you the quark's trajectory. The composition of particles in the jet tells you about the fragmentation process, about how the flux tube snapped and what particles were created. Jets are the fingerprints that quarks leave behind, and reading those fingerprints is one of the major activities of experimental particle physics. The process of quarks turning into jets of hadrons is called hadronization or fragmentation. It's the mechanism by which confinement enforces itself in practice. Every time a quark tries to escape, hadronization drags it back, converting its energy into new particles rather than allowing it to exist in isolation. Hadronization is also one of the most computationally difficult aspects of QCD to model. While the behavior of quarks at short distances, where the force is weak, can be calculated precisely using a technique called perturbative QCD, the hadronization process happens at longer distances, where the force is strong. In this strong coupling regime, the standard mathematical tools of quantum field theory break down. The calculations become so complex that no one has figured out how to solve them exactly. Physicists rely on computer simulations and approximate models to describe hadronization, and these models work remarkably well in practice. But a fully rigorous mathematical derivation of confinement from first principles remains one of the greatest unsolved problems in theoretical physics. And it's a mystery we haven't finished exploring yet. Let me tell you about some of the most dramatic experimental evidence for the behavior of the strong force. Because the story of how physicists confirm these ideas is as fascinating as the ideas themselves. The first direct evidence for jets, and therefore for the existence of quarks inside protons, came from the Spear Collider at the Stanford Linear Accelerator Center in the mid-1970s. In these experiments, electrons and positrons were collided at high energies. The electron and positron would annihilate each other, converting into a burst of pure energy, which then materialized as a quark-antiquark pair. These quarks couldn't exist freely, so they immediately hadronized, producing two jets of particles flying off in opposite directions. The observation of these two jet events was powerful evidence that quarks were real physical objects that could be produced in collisions, and that confinement then turned them into jets of hadrons. Then, in 1979, something even more exciting happened at the Petra Collider at the DSY laboratory in Hamburg, Germany. Physicists observed events with not two, but three jets. This was a landmark discovery because the third jet corresponded to a gluon. In these events, one of the quarks had radiated a high-energy gluon before hadronizing, much like an electrically charged particle can radiate a photon. The gluon, being a colored particle, also couldn't exist freely. It too hadronized, creating its own separate jet of particles. The observation of three jet events was the first direct experimental evidence for the existence of gluons. Gluons were no longer theoretical constructs needed only to make the mathematics work. They were real particles that left real, measurable signatures in the detector. You could point to a spray of particles on a computer screen and say with confidence, that jet was made by a gluon. This discovery confirmed the core prediction of quantum chromodynamics, but perhaps the most spectacular experimental exploration of the strong force involves something called the quark-gluon plasma. Remember, I said that the strong force gets weaker at short distances and stronger at long distances. This means that under normal conditions, at the relatively low temperatures and densities of everyday matter, quarks are confined inside protons and neutrons. But what if you could create conditions of extreme temperature and density? What if you could heat matter to such incredible temperatures that the quarks inside protons and neutrons gained so much energy that the distances between them became irrelevant? At sufficiently extreme conditions, the strong force would become so weak that quarks would no longer be confined. They would move freely, no longer bound inside individual protons and neutrons. Matter would melt into a new phase, a plasma of free quarks and gluons, all mixing together in a hot, dense soup. This state of matter is called the quark-gluon plasma, and it's not just theoretical speculation. Physicists have created it in laboratories on Earth. The Relativistic Heavy Ion Collider, or RHIC, at Brookhaven National Laboratory on Long Island, New York, began operating in 2000. RHIC collides gold nuclei at nearly the speed of light. Each gold nucleus contains 79 protons and 118 neutrons. When two gold nuclei smash into each other, the collision involves hundreds of protons and neutrons all crashing together simultaneously. The energy density at the center of the collision is so extreme, the temperature so incredibly high, that for a brief, fleeting instant, the quarks and gluons inside the protons and neutrons are liberated from confinement. The temperatures created in these collisions are staggering. The quark-gluon plasma at RHIC reaches temperatures of about 4 trillion degrees Celsius. That's roughly 250,000 times hotter than the center of the sun. At these temperatures, protons and neutrons literally melt. The quarks and gluons that were trapped inside them spill out and mingle freely, forming a state of matter that hasn't existed naturally in the universe since about 1 microsecond after the Big Bang. For a few millionths of a billionth of a second, a tiny droplet of quark-gluon plasma exists in the collision zone. Then it cools rapidly. The strong force reasserts its dominance, and the quarks and gluons reconfine into ordinary hadrons that fly outward and are detected by the instruments surrounding the collision point. What surprised physicists at RHIC was that the quark-gluon plasma didn't behave the way they expected. Theoretical models had predicted it would behave like a gas, with quarks and gluons bouncing around independently like molecules in steam. The expectation was that deconfined quarks, freed from the flux tubes that normally bind them, would zip around essentially as free particles, colliding occasionally but mostly traveling independently. Instead, the quark-gluon plasma behaved like a nearly perfect liquid, a fluid with almost zero viscosity. It flowed collectively, with quarks and gluons moving together in coordinated patterns rather than independently. The quark-gluon plasma flows with less internal friction than any other substance ever measured. Less than liquid helium, less than any superfluid ever created in a laboratory. This discovery, announced around 2005, sent shockwaves through the theoretical physics community. It challenged existing models and required entirely new theoretical approaches to explain. It showed that even when quarks are deconfined, even when the flux tubes have melted away, and quarks are no longer locked inside individual protons and neutrons, the strong force still mediates significant interactions between them. The quarks aren't truly free even in the plasma. They're strongly coupled, interacting constantly and flowing together as a collective, almost frictionless fluid. The strong force never really lets go. Even in its weakest regime, it still shapes matter profoundly. The Large Hadron Collider at CERN has taken these experiments even further. In dedicated heavy ion runs, the LHC collides lead nuclei at even higher energies than RHIC, creating hotter and longer-lived droplets of quark-gluon plasma. The ALICE detector at the LHC was specifically designed to study this exotic state of matter. Results from the LHC have confirmed and extended the RHIC findings, showing that the quark-gluon plasma is indeed a nearly perfect liquid and revealing additional details about its properties. These experiments are recreating conditions that existed during the first microsecond of the universe's existence. In the standard model of cosmology, the entire universe was filled with quark-gluon plasma for roughly the first microsecond after the Big Bang. The temperature was so extreme, trillions of degrees, that quarks and gluons existed freely, not confined inside protons and neutrons. The universe at that moment was a vast, seething ocean of deconfined quarks and gluons filling all of space. There were no protons, there were no neutrons, there were no atoms, Just quarks and gluons and a handful of other particles, all swimming freely in a plasma denser and hotter than anything that exists in the universe today. As the universe expanded and cooled over the next millionths of a second, the temperature dropped below the critical threshold of roughly 2 trillion degrees Celsius, and confinement switched on. The strong force reasserted its grip. Quarks combined into protons and neutrons, and the ordinary matter we know today formed from this primordial plasma. The protons and neutrons that make up your body were assembled from quarks that were once free, swimming in the quark-gluon plasma that filled the newborn universe. Confinement locked them in, and they've been locked in ever since for the last 13.8 billion years. Every time physicists create quark-gluon plasma in a collider, they're briefly undoing one of the most fundamental transitions in cosmic history. They're temporarily freeing quarks from the confinement that the cooling universe imposed on them billions of years ago, and every time the plasma cools and the quarks reconfine, they're watching a miniature replay of one of the most important events in the history of the universe, the moment when free quarks became imprisoned matter. There's something else that particle collider experiments have revealed about the strong force. Something subtle but deeply important. When physicists measure the strength of the strong force at different energy scales, they find that it changes exactly as QCD predicts. At low energies corresponding to long distances, the force is strong. At high energies corresponding to short distances, the force is weak. This behavior has been measured across an enormous range of energies, from relatively low energy experiments, studying the properties of hadrons, to extremely high energy collisions at the LHC. Across this entire range, spanning several orders of magnitude in energy, the measured strength of the strong force matches the predictions of QCD with remarkable precision. This is called the running of the coupling constant, and it's one of the most compelling pieces of evidence that QCD is the correct theory of the strong force. The strong coupling constant, usually denoted by the Greek letter alpha sub s, decreases logarithmically with increasing energy. At the energy scales of the LHC, the strong coupling constant is about 0.12, meaning the force is relatively weak and perturbative calculations work well. At the energy scale of a proton's mass, the coupling constant grows to around 1, meaning the force is genuinely strong and perturbative methods break down. Below that scale, the coupling constant continues to grow, and confinement takes hold. This running of the coupling constant also has a fascinating implication that connects the strong force to one of the great dreams of theoretical physics: the unification of forces. When physicists plot the strengths of the 3 non-gravitational forces, electromagnetism, the weak force, and the strong force as functions of energy, something remarkable appears. At low energies, the 3 forces have very different strengths. The strong force is the strongest by far at nuclear scales. The electromagnetic force is next. The weak force is the weakest of the 3, though still far stronger than gravity. But as you go to higher and higher energies, the 3 coupling constants converge. The strong coupling constant decreases because of asymptotic freedom. The electromagnetic coupling constant increases slowly because of vacuum screening. The weak coupling constant also changes with energy in a specific way predicted by theory. At extremely high energies, around 10 to the 15 times the energy of a proton mass, the 3 forces become roughly equal in strength. They nearly meet at a single point. This near convergence is tantalizing because it suggests that the three forces might actually be different aspects of a single underlying force. At very high energies that existed in the earliest moments of the universe, all three forces might have been unified into one grand force. As the universe cooled, this grand force broke apart, splitting into the three separate forces we observe today, each with its own strength and its own behavior. This idea is called grand unification, and it's been a driving goal of theoretical physics for decades. Several grand unified theories have been proposed, and some of them predict that the three coupling constants should converge at exactly the same point. The fact that they nearly do, but not quite in the simplest models, is both encouraging and frustrating. It suggests we're on the right track, but haven't found the final answer yet. Some extensions of the standard model, particularly supersymmetry, predict that the coupling constants converge more precisely, but supersymmetry has not yet been confirmed experimentally despite extensive searches at the LHC. Returning to confinement, there's one more aspect to this phenomenon that deserves attention because it connects to something deeply practical. The flux tube model of confinement, where gluon field lines squeeze into a narrow string connecting quarks, has inspired an entire branch of theoretical physics called string models of hadrons. In the early 1970s, before QCD was fully developed, physicists noticed that the properties of hadrons could be described remarkably well by treating quarks as endpoints of vibrating strings. The different vibrational modes of the string corresponded to different hadron states, with different masses and spins. This string model works surprisingly well, and it later evolved into what we now know as string theory, one of the leading candidates for a theory of quantum gravity. The connection is fascinating. The physical flux tubes of QCD, real objects made of compressed gluon fields, inspired a mathematical framework that eventually became a candidate for a theory of everything. The strong force, with its peculiar confinement mechanism, didn't just shape the structure of matter, it shaped the direction of theoretical physics itself. So let me bring all of this together. The strong force, through confinement, ensures that quarks can never exist alone. When quarks try to separate, the gluon field between them forms a flux tube that stores energy proportional to its length. When enough energy accumulates, the tube snaps and new quarks are created from the stored energy. This process means that you can never isolate a single quark, no matter how much energy you invest. The universe will always create new quarks, rather than allow a free one to exist. This has been confirmed by decades of experiments at particle colliders around the world. Jets of particles, produced by the hadronization of quarks, knocked free in high-energy collisions, are observed daily at facilities like CERN. The quark-gluon plasma, a state where confinement is temporarily overcome by extreme temperatures, has been created at RHIC and the LHC, revealing that even deconfined quarks interact strongly, forming a nearly perfect liquid. And the running of the strong coupling constant, measured across a huge range of energies, matches QCD predictions with extraordinary accuracy. The strong force is not like the other forces. It creates prisons that cannot be escaped. It builds walls that grow stronger the harder you push against them. It creates new matter rather than releasing the particles it holds. And it does all of this through one simple mechanism. Gluons carry color charge. That single property, the self-interaction of the force carriers, is responsible for asymptotic freedom, for confinement, for flux tubes, for jets, for the quark-gluon plasma, And ultimately, as we're about to discover, for the very existence of mass itself and for everything that exists in the physical universe. Now we arrive at the consequence of the strong force that matters most to you. Not in some abstract, distant, theoretical way, in the most personal, physical, tangible way possible. Because everything we have explored so far, the gluon self-interaction, the asymptotic freedom, the confinement, the flux tubes, the jets, the quark-gluon plasma, all of it leads to a single stunning realization about the nature of mass. Your mass. The mass of everything around you. The mass of the Earth, the sun, the stars, and every physical object in the known universe. Nearly all of it, roughly 99% of it, comes from the strong force. Not from the substance of particles, not from some inherent heaviness of matter, from energy. Energy trapped inside protons and neutrons by the unbreakable grip of the gluon field. And to understand why, we need to confront a profound misconception that most people carry about where mass actually comes from. If you've heard anything about the origin of mass, you've probably heard of the Higgs boson. The Higgs boson was discovered at the Large Hadron Collider at CERN in 2012, and the announcement made headlines around the world. Peter Higgs and Francois Englert received the 2013 Nobel Prize in Physics for predicting the existence of the Higgs field decades before it was experimentally confirmed. The Higgs field is a quantum field that permeates every corner of the universe. When certain fundamental particles move through this field, they interact with it, and that interaction gives them mass. Without the Higgs field, those particles would be massless, zipping through space at the speed of light like photons. The Higgs field creates a kind of resistance, a drag, that slows them down and gives them the property we call mass. This is the Higgs mechanism, and it is real. It has been confirmed experimentally. It is one of the great achievements of modern physics. But here is what almost nobody realizes. The Higgs mechanism is responsible for less than 1% of the mass of ordinary matter. Let that settle for a moment. The Higgs boson, the so-called God particle, the discovery that was hailed as one of the greatest triumphs of 21st century physics, accounts for less than 1% of the mass of the stuff you're made of. Less than 1% of the mass of the chair you're sitting on, the phone in your hand, the planet beneath your feet. The Higgs mechanism gives quarks their intrinsic mass, but those intrinsic masses are astonishingly tiny. An up quark has a mass of about 2.2 mega electron volts, a down quark about 4.7 mega electron volts. A proton is made of 2 up quarks and 1 down quark. Add up the Higgs generated masses of those 3 quarks, and you get roughly 9.1 mega electron volts. But the measured mass of a proton is 938.3 mega electron volts. The quarks contribute less than 1% of the proton's mass. The Higgs field, for all its celebrity, for all the billions of dollars and decades of effort spent confirming its existence, is responsible for a tiny sliver of the mass of ordinary matter. So where does the other 99% come from? It comes from the strong force. It comes from Einstein's equation, E equals mc squared, applied to the roiling inferno of energy inside every proton and neutron in the universe. Inside a proton, the 3 quarks are not sitting quietly in fixed positions like billiard balls in a rack. They are confined within a space about 1 femtometer across, 1 quadrillionth of a meter, and they are moving at velocities close to the speed of light. They ricochet around inside this impossibly small prison with tremendous kinetic energy, constantly changing direction as they interact with the gluon field surrounding them. Meanwhile, the gluon field between them is in a state of constant violent activity that defies easy description. Gluons are being emitted and absorbed at a furious rate, millions upon millions of times every second. Because gluons carry color charge and interact with each other, they don't just shuttle back and forth between quarks. They spawn new gluons, which spawn more gluons, which interact and merge and split in a turbulent cascade of energy. Virtual quark-antiquark pairs pop in and out of existence within this storm, appearing for the briefest of instants before annihilating back into the gluon field. The inside of a proton is not a calm, static structure. It is a seething hurricane of quantum activity, one of the most energetically dense environments in the universe, compressed into a volume smaller than an atomic nucleus. All of this energy has mass. That is what Einstein's equation means. Energy and mass are two faces of the same coin. E equals mc squared tells us that energy has a mass equivalent, and mass is a form of stored energy. The enormous kinetic energy of the quarks bouncing around at near light speed has mass. The energy of the gluon field, constantly churning and self-interacting, has mass. The energy of virtual particles winking in and out of the vacuum inside the proton has mass. Add all of this energy up, convert it to mass through Einstein's equation, and you get roughly 99% of the proton's mass. The proton is heavy not because its constituent quarks are heavy. They're almost massless. The proton is heavy because the energy of its internal dynamics, the energy of quarks and gluons bound by the strong force, is enormous. This is a staggering idea. Think about what it means for you personally. Your body is composed of atoms. Those atoms are composed of electrons orbiting nuclei. The nuclei are composed of protons and neutrons. The electrons contribute a negligible fraction of your total mass. The intrinsic quark masses contribute less than 1%. Roughly 99% of your body mass is the energy of the strong force, manifested as mass through Einstein's equation. You weigh what you weigh not because of the stuff you're made of, not because your constituent particles are inherently heavy, but because of the energy trapped inside your protons and neutrons. You are, in the most literal physical sense, made of bound energy. Energy that the strong force will not release. Energy that has been locked inside protons and neutrons since the first microsecond after the Big Bang, 13.8 billion years ago. Every kilogram of your body contains a mere sliver of matter and an overwhelming majority of pure energy, imprisoned by the most tenacious force in existence. If the strong force could be switched off, if some cosmic hand could reach into the laws of physics and disable it, the consequences would be instant, total, and irreversible. Every proton and neutron in the universe would lose nearly all of its mass. They would become almost weightless phantoms, ghosts of their former selves. Atomic nuclei would disintegrate immediately because the force binding them would no longer exist. The electromagnetic repulsion between protons, held in check for billions of years by the strong force, would finally win. Protons would scatter apart. Atoms would fly to pieces. The complex architecture of chemistry, the intricate dance of electrons around nuclei that gives rise to molecules, materials, and life would vanish. The sun would stop burning because nuclear fusion requires the strong force to bind the products of fusion into stable nuclei. Without fusion, the sun's core would collapse under gravity and then disperse. Stars across the universe would suffer the same fate. Planets would dissolve into expanding clouds of nearly massless debris. Every structure in the universe, from grains of sand to galaxy clusters, would simply cease to exist as coherent physical objects. The cosmos would become a thin, cold, dark, structureless fog of nearly weightless particles, drifting silently through infinite space, never combining, never interacting in any meaningful way, never creating anything ever again. The strong force is not merely one of the four fundamental forces. It is the reason matter has mass. It is the reason the physical world has substance. Every time you feel the weight of something in your hand, every time you stand on solid ground, every time you feel your own body pressing down against a chair, you are feeling the strong force at work. Not directly, of course. You can never feel the strong force directly. It operates on scales too small to ever touch. But its consequences are the most tangible thing in the universe. Mass, weight, solidity, all of it created by the energy of quarks and gluons, bound by a force that never lets go. Now, there is something deeply thought-provoking about this picture. Something that keeps theoretical physicists awake at night and fuels passionate debate at conferences around the world. The strength of the strong force appears to be exquisitely calibrated. Not approximately calibrated. Not roughly in the right range. Exquisitely, precisely calibrated. If it were different from its actual value by even a modest amount, the universe would be radically altered. And in most scenarios, life as we know it would be completely impossible. Imagine the strong force were just a few percent weaker. At a slightly reduced strength, quarks would still bind into protons and neutrons, but certain light nuclei would become unstable. Deuterium, the nucleus made of one proton and one neutron, is only barely held together by the strong force. Its binding energy is small compared to heavier nuclei. A slightly weaker strong force might make deuterium unstable. This matters enormously because deuterium is the essential first stepping stone in stellar nuclear fusion. Inside, stars like the Sun, the fusion process begins when two protons combine to form a deuterium nucleus. This is the gateway reaction. Every heavier element produced in stars, every atom of carbon, oxygen, nitrogen, and iron that eventually makes its way into planets and living beings, traces its ancestry back to this first step. If deuterium couldn't form or couldn't survive long enough to participate in subsequent reactions, the entire chain of stellar nucleosynthesis would be broken. Stars might still shine through other mechanisms, but the rich variety of chemical elements that makes complex chemistry and biology possible might never be produced. Now imagine the opposite. A strong force just a few percent stronger. In this scenario, two protons could bind directly to each other, without needing to first convert one of them into a neutron through the weak force. This would be catastrophic for the universe. In the first few minutes after the Big Bang, during the era of primordial nucleosynthesis, a stronger force would cause nearly all hydrogen in the universe to fuse rapidly into heavier elements. Hydrogen would become scarce or disappear entirely. This would be a disaster of cosmic proportions. Hydrogen is the fuel that powers ordinary stars. Hydrogen is one of the two elements in water. Hydrogen is a core component of organic molecules. A universe starved of hydrogen would be a universe without long-lived stars, without water, without the molecular foundations of life. It would be a sterile, barren cosmos. The strong force sits in a narrow corridor of values that permits the universe as we know it. Strong enough to bind protons and neutrons into the nuclei of 100 different elements, enabling the extraordinary chemical diversity of the periodic table, but not so strong that all hydrogen is consumed before stars and planets have a chance to form. This apparent fine-tuning is one of the most fascinating and debated observations in physics. Some physicists interpret it as evidence for a multiverse, a vast collection of universes with different physical constants, where we inevitably find ourselves in one of the rare configurations compatible with observers. Others believe that a deeper, undiscovered theory will someday explain why the strong force has exactly the strength it does, revealing that what looks like fine-tuning is actually the inevitable consequence of some more fundamental principle we haven't yet grasped. The honest answer is that we don't know which interpretation is correct. The question remains wide open. This brings us to the frontiers of strong force research, where some of the most profound unsolved problems in all of science still await resolution. Because despite everything we've learned about QCD, despite its spectacular success in predicting experimental results, there are deep aspects of the strong force that remain mysterious. The single most famous unsolved problem is the mathematical proof of confinement. Everything we've discussed about quarks being permanently imprisoned, about flux tubes snapping to create new particles, about the impossibility of isolating a free quark, all of this is observed experimentally and reproduced in computer simulations. But no one has ever proven it mathematically from the fundamental equations of QCD. No one has started with the Lagrangian of quantum chromodynamics, the master equation that encodes the entire theory in a single line of mathematical notation, and derived, through rigorous logical deduction, the conclusion that confinement must occur. This isn't some minor technical gap, some loose end waiting to be tied up by a graduate student. It is one of the 7 Millennium Prize Problems designated by the Clay Mathematics Institute in the year 2000. These are considered the 7 most important unsolved problems in all of mathematics, and each carries a prize of $1 million for its solution. In the 26 years since the prize was established, only one of the 7 problems has been solved. The strong forces problem is not the one that was solved. The specific problem is called the Yang-Mills existence and mass gap problem. Yang-Mills theories are the class of mathematical structures that underlie QCD and the electroweak theory. The mass gap refers to the fact that the lightest particles described by QCD, the pions, have non-zero mass, proving that a Yang-Mills theory like QCD necessarily produces a mass gap would be tantamount to proving confinement from first principles. It would mean showing that the mathematics of the theory demands that quarks be confined, not merely observing that they are. It would elevate our understanding of confinement from an empirical fact to a mathematical certainty. Some of the most brilliant mathematical physicists in history have attempted this problem over the course of decades. None have succeeded. It may be solved next year, it may take another century. The strong force does not yield its deepest secrets easily. In the meantime, physicists have developed an extraordinarily powerful computational method for studying QCD in the confinement regime. It's called lattice QCD. The fundamental idea is elegant in its simplicity, even though the execution is staggeringly complex. Since no one can solve the equations of QCD exactly when the force is strong, physicists instead discretize space-time. They replace the smooth, continuous fabric of space and time with a grid, a lattice of discrete points separated by tiny intervals. Quarks are placed on the lattice points. Gluon fields are placed on the links connecting neighboring points. Then, using supercomputers, physicists simulate how the quarks and gluons interact on this lattice. They average over billions of possible configurations of the gluon field, weighted by their probability, to calculate physical quantities like the masses of hadrons, the decay rates of unstable particles, and the internal structure of protons and neutrons. The results of lattice QCD are nothing short of extraordinary. Starting from just a handful of input parameters, the quark masses and the strong coupling constant, lattice calculations have predicted the masses of protons, neutrons, pions, kaons, and dozens of other hadrons. These predictions match experimental measurements to within a few percent accuracy, and in some cases to within fractions of a percent. A landmark lattice QCD calculation published in 2008 by a collaboration of European and American physicists computed the masses of the proton, neutron, and several other light hadrons from first principles, achieving agreement with experiment at the 1 to 2% level. This was a watershed moment in physics. It meant that the mass of the proton, which determines most of the mass of the visible universe, could be derived directly from the fundamental theory. It meant that QCD, when solved computationally, produces the physical world we actually observe. It confirmed that the source of mass is exactly what physicists had suspected: the energy of quarks and gluons bound by the strong force. The mass of your body can, in principle, be calculated from a single equation, and the answer is correct. But lattice QCD has its limitations. The computations are enormously expensive. A single state-of-the-art lattice calculation can require months of continuous runtime on the world's most powerful supercomputers, machines with thousands of processors working in parallel. The lattice spacing must be made finer and finer to reduce discretization errors, and this demands ever-increasing computing power. Certain types of calculations remain exceptionally difficult. Simulations at high baryon density, which are needed to understand the interiors of neutron stars, suffer from a notorious technical obstacle called the sign problem that makes standard lattice methods unreliable. Real-time dynamical processes are also extremely challenging to simulate on a lattice. Despite these limitations, lattice QCD remains our most powerful tool for studying the strong force, where it matters most, in the regime where confinement lives and where the mass of matter is generated. And speaking of neutron stars, these extreme objects represent one of the most exciting frontiers of strong force research today. When a massive star exhausts its nuclear fuel and its core collapses under gravity, the result can be a neutron star, an object roughly 12 miles across, but containing 1 to 2 times the mass of our entire sun. A single teaspoon of neutron star material would weigh about 6 billion tons on Earth. Inside a neutron star, matter is compressed to densities that exceed those of an atomic nucleus. Neutrons are packed so tightly that they nearly overlap. The strong force is operating under conditions utterly unlike anything inside an ordinary atom. The boundaries between individual neutrons blur. Quarks inside, adjacent neutrons begin to interact directly with each other, and the neat picture of well-separated nucleons dissolves into something far more exotic. Some theoretical models predict that at the very cores of the most massive neutron stars, densities reach a level where neutrons themselves dissolve. The quarks inside them become deconfined, forming a new phase of cold, dense quark matter, unlike anything ever created in a laboratory. This wouldn't be the hot quark-gluon plasma produced in heavy ion colliders, which exists at trillions of degrees for fractions of a second. It will be quark matter at temperatures close to absolute zero, but at pressures beyond anything we can produce on Earth. Pressures created by the crushing weight of an entire star compressed into a space the size of a city. Some theories suggest this cold quark matter could form an exotic state called a color superconductor, where quarks form pairs analogous to how electrons pair in ordinary superconductors, producing remarkable and unprecedented properties like the frictionless flow of color charge. If color superconducting quark matter exists at the hearts of neutron stars, it would represent an entirely new phase of matter, one that exists nowhere else in the present-day universe. We are beginning to test these ideas observationally. The detection of gravitational waves from the merger of two neutron stars by the LIGO and Virgo observatories in 2017, designated GW170817, opened a revolutionary new window into neutron star interiors. This event was the first ever observation of gravitational waves from a neutron star merger, and it was simultaneously observed across the electromagnetic spectrum, from gamma rays to radio waves. When neutron stars spiral toward each other and collide, the gravitational waves they emit carry information about how the stars deform under tidal forces, which depends directly on their internal composition. Future gravitational wave detections, combined with X-ray observations from telescopes like NIXA aboard the International Space Station, may finally tell us whether quark matter exists inside neutron stars. This would be a discovery of enormous significance, revealing a new state of matter shaped by the strong force under conditions we cannot reproduce on Earth, and answering questions about the behavior of QCD in an entirely unexplored regime. So where does this journey leave us? What should we carry away from this exploration of the strongest force in nature? We began with a simple question: what is the strongest force? And we discovered that the question itself is more nuanced than it first appears. At the scale of atomic nuclei, the strong force overwhelms electromagnetism, holding protons together despite their electrical repulsion. At cosmic scales, gravity dominates because it acts on every particle of mass, accumulating over trillions of atoms to hold galaxies together and shape the structure of the universe. There is no single strongest force in all contexts. Each force has its domain, its arena, its range of scales where it reigns supreme. But what makes the strong force unique is not merely its strength at nuclear distances. It is the way that strength behaves. Every other force weakens with distance. The strong force strengthens. Every other force allows separation. The strong force forbids it. Every other force pushed hard enough can be overcome. The strong force pushed hard enough creates new matter rather than yielding. These properties aren't just curiosities. They are the reason mass exists, and mass is the foundation of everything. Without mass, gravity has nothing to act on. Without gravity acting on mass, there are no galaxies, no stars, no planets. Without planets, there are no oceans, no continents, no ecosystems. Without a complex chemistry that mass makes possible, there are no molecules, no cells, no living things. The entire physical universe, every structure from atoms to superclusters of galaxies, rests on the foundation of mass. And that mass, 99% of it, is the gift of the strong force, energy made solid, motion made permanent, the fury of quarks and gluons, frozen into the heft and substance of the world you inhabit. You have never felt the strong force directly. It operates entirely within the nucleus, on scales so small that the entire nucleus is 100,000 times smaller than the atom it inhabits. If an atom were expanded to the size of a city, the nucleus where the strong force operates would be no larger than a sugar cube sitting at the center. And yet that sugar cube would contain virtually all the mass of the entire city. That is the paradox. The most powerful force at subatomic scales, the force responsible for almost all the mass in the universe, is invisible, hidden, confined to a realm so small that no microscope will ever directly image it. It does its work in absolute secrecy, generating the mass that makes the universe tangible while remaining forever beyond the reach of direct human experience. The ancient philosophers wanted to know what the world was made of. They proposed earth, water, air, and fire. Democritus came closer with his idea of atoms, indivisible building blocks combining in endless ways, but none of them could have imagined the truth. That the substance of reality, the mass of matter, the weight of the world, doesn't come from any fundamental stuff at all. It comes from energy. The energy of quarks moving at nearly the speed of light. The energy of gluons constantly erupting and interacting. The energy of a force so determined to keep its prisoners bound that it would rather create new matter from raw energy than let a single quark walk free. Every proton in your body has endured since the universe was 1 microsecond old. For 13.8 billion years, the strong force has held the quarks inside those protons in its grip. Stars have been born and died in that time. Galaxies have formed and collided. The universe has expanded to a scale almost beyond comprehension. And through all of it, the strong force has never loosened its hold. Not once. Not by the smallest fraction. The quarks inside your protons are as tightly bound right now as they were in the first moment of their confinement, in the primordial plasma of the infant universe. And here is what I find most remarkable about the strong force. In a universe that seems, on the larger scales, designed for emptiness, for vast cold spaces between distant galaxies, for isolation and silence stretching across billions of light years, there is this force operating on the smallest scales that refuses to allow isolation. A force that insists on togetherness. A force that, when confronted with the possibility of a particle existing alone, says no and creates a companion from pure energy. The deepest force in nature is a force of mandatory connection. A force that answers every act of separation with an act of creation. A force that will not permit loneliness at the most fundamental level of reality. We set out to find the strongest force. What we found was something far stranger and far more beautiful. A force that breaks every intuitive rule about how forces should behave. A force that creates nearly all the mass in the visible universe from pure energy. A force that has held matter together since the first microsecond of cosmic history and will continue holding it together long after our sun has burned out and our galaxy has merged with Andromeda. The strongest force in nature isn't what you thought. It's weirder, more wonderful, and more essential than you ever imagined. It is inside you right now, generating the mass that gives you a body, giving you weight and substance and physical presence in the cosmos. Thank you for coming on this journey with me. Next time you pick something up and feel its weight, remember, you are feeling the strong force. 99% of that weight is the energy of quarks and gluons, imprisoned since the dawn of time by the most extraordinary force in nature. It holds you together. It holds everything together. Silently, invisibly, and absolutely. Good night.